This is the 44th lecture and problem session 10. We are going to work out problems on LC driving point synthesis. Someone else who came late, you can pick up from here. Problems on LC driving point synthesis. And in the problems that I have circulated to you, we start with problem 11.2. The first one is skip. 11.2 says, indicate the general form of two Foster and two cover networks F1, F2, C1, C2. Only general forms are needed. That could be used to synthesize the following LC impedance. Z of S equals to S squared plus 1, S squared plus 9, S squared plus 25, and the denominator S times S squared plus 4, S squared plus 16. There is no need to calculate the element values of the four networks, just the general form you have to draw. And one proceeds like this. Foster 1, ask yourself whether there is a pole at infinity. Yes, there is. So you shall have an inductance. Is there a pole at the origin? Yes, there is. There is a pole at the origin. So there is a capacitance. And there are two pairs of internal poles corresponding to four elements, and so two LC networks in parallel. Two LC parallel networks in series. And that is it. This is the general form. As a verification, you check whether the number of elements is equal to the number of specs. Specs are 1, 2, 3, 4, 5 and the multiplying constant which happens to be 1. So 6 specs, there are exactly 6 elements. For F2, you take the admittance function. Y of S is equal to S times S square plus 4, S square plus 16, S square plus 1, S square plus 9, S square plus 25. No pole at the origin, no pole at infinity. It cannot have because the impedance had these poles, therefore admittance must have zeros, and therefore all we have is 3 series resonance circuits in parallel. That is it, exactly 6 elements. Can you tell me what these products of LC would be? This LNC, this will be 1, then next one 1/9 and 1/25. Okay. So this is the general form for F2. Now C1 starts with, can you start with impedance? Shall we start with impedance or admittance? C1, that is the point to be decided. The function has to have a pole at infinity, and therefore it is the Z of S, and there are exactly 6 elements, and therefore you start with an inductance, pole at infinity, then a capacitance, and you go on doing this till you get 6 elements. That is it, you can do it blindly. As a check, does it satisfy the condition that there is a pole at the origin? That is, we are checking the last element. Is the last element a capacitor? Yes, there is a pole at the origin, therefore this is the correct network. All right. In order to get C2, C2, we will start with the function that has a pole at the origin, which means the impedance function. Yeah.
So if we had 6 elements and we didn't have a pole at infinity.
If we had 6 elements, we didn't have a pole at infinity. Well, then the position at
so it's a pole at 0 but a pole at infinity.
Pole at the origin, but no pole at infinity. Okay, then we start with the capacitance. We cannot have 6 elements then. It has to be odd number of elements. Okay. There are various checks. This is one of the checks. There are other checks also. Okay. As far as C2 is concerned, you have to start with impedance. You have to start continued fraction expansion with the lowest powers starting from impedance. Therefore, you have a capacitor in series, and then you go on doing the ladder till you get 6 elements, and finally at infinity does it have a pole? Yes, it does. Okay, so that is a check. That is 11.2. Let us go to 11.3, which is very interesting. And that is why I did not skip one, I wanted to do 11.3. 11.3 says synthesize the LC driving point impedance. The impedance is given, Z of S equals to 6 S to the 4th plus 42 S squared plus 48 divided by S to the 5 plus 18 S cubed plus 48 S. It says synthesize this LC driving point impedance in the form shown in the figure. The architecture is given. Architecture is you have a capacitor, then an inductor, then a parallel LC, and finally a capacitor. C1, L1, C2, L2, C3. The architecture is given. Okay. Now, you can see that it is neither Foster 1 nor Foster 2 nor cover 1 nor cover 2. It is a combination. It is a combination. You can mechanize this. You can start with cover 2, go up to 2 stages, and then the rest of the function goes to Foster 1. All right. You can do that, or you can do it by successive pole removal. That is no, but before that, is this a valid architecture? Is this a valid architecture? Well, how many specifications are there? 1, 2, 3, 4, 5, 6. There are exactly 6 elements. No. 5 specs? This is not a spec? Yeah, we can take 6 common constant, then we have S to the 4 and in the denominator S to the 5. So, there are 4 other constants. You have exactly 5. It is a valid architecture. No, not so easily. Is there a pole at the origin? Yes, there is a pole at the origin, so it is. Infinity? Is it a 0 at infinity? Yes, it is. This is short, this is short, this is short, and therefore there is. So, this is a valid architecture. The number of elements is satisfied, pole at infinity, pole at the origin. Yes. Okay. By looking at the function, what is not clear? The number of elements? Okay. Number of elements, you can write this as 6 times S to the 4 plus 7 S squared plus 8 divided by S to the 5 plus 18 S cubed plus 48 S. So, the number of specs is 1, 2, 3, 4, 5, and there are exactly 5 elements. All right. Then we check whether there is a pole at the origin. Yes, the structure has a pole at the origin. We check whether there is a 0 at infinity. Yes, it has a 0 at infinity. Okay. Now, as someone said, we can develop this by having cover 2 up to 2 stages, then changing over to Foster 1. Well, we can do that. This is a mechanization, okay, but the the procedure that is foolproof, you cannot make a mistake. Suppose instead of Foster 1, suppose instead of cover 2, okay, you use cover 1. Well, you cannot use it, but suppose you make a mistake in the continued fraction, or finally its inversion. You see, the remainder impedance that you take, it must be of the proper dimension and so on. What I am saying is there may be a possibility of a confusion or a mistake, but the foolproof method is if you go term by term. That is, first you look at this z of s equal to 6 s to the 4th plus 42, and the effort involved is nothing much higher. Effort involved is almost the same, and things come out almost by inspection. Okay, look at this: s to the 5 plus 18 s cubed plus 48 s. What you are trying to do is you are writing z of s as equal to its pole at the origin, which is obviously 1 by s. Agreed? Pole at the origin, that is, if you put s equal to 0, 48 by 48 s. So the residue is obvious, plus some impedance z1, and you can see that z1 is s to the 5 plus 18 s cubed plus 48 s, and the numerator you shall have 6 s4 plus 42 s squared plus 48 minus z1 is z minus 1 over s. So you have to take s out of here, s to the 4th minus 18 s squared minus 48, and you see that 48 and 48 cancel, they have 2. There is no other way, because you are removing the pole at the origin, there must be a 0 at the origin for the remainder function. So these 2 cancel, and I get 5 s to the 4th plus 24 s squared divided by s to the 5 plus 18 s cubed plus 48 s. That is more in store, more cancellation, because the pole at the origin has been taken away. So the factor s should cancel, and if I do that, then my my function that remains is 5 s cubed plus 24 s squared divided by s fourth plus 18 24 s, correct, s to the 4 plus 18 s squared plus 48. Okay. Now no, 18 s squared, okay, s squared, because s is cancelled. Now what I have removed therefore is a 1 farad capacitor, and the rest of the function is z1. What we have to remove now is an inductor. I require an inductor. An inductor in shunt represents a pole of the admittance at the origin, and therefore what I should do is take y1. In fact, z1 has a 0 at the origin, so you invert it. I get y1 equal to s4 plus 18 s squared plus 18 divided by 5 s cubed plus 48. Okay, don't allow me to make a mistake. 24s, and I am going to write this as k by s, which is obviously 2 by s plus y2, which means that the next inductor is half Henry, and the rest of the admittance is y2. All right. Now let us see what is y2. y2 is y1 minus 2 by s. So this is equal to s5 s cubed plus 24 s, then s to the 4th plus 18 s squared plus 48 minus, you take out s from here and multiply by 2. So you get 10 s squared, agreed, minus 48. Once again you see that the constant terms cancel. So it's quite comfortable. 48 cancels, and then you get s to the 4th plus 8 s squared divided by 5 s cubed plus 24 s, from which s shall also cancel. So you get s cubed plus 8s divided by 5s squared plus 24. Okay, and after y2, now you are perfectly safe to shift to Foster 1, because you look at the function Z2, Foster 1 means you take the impedance Z2, which is equal to 5s squared plus 24 divided by s times s square plus 8. There is indeed a pole at the origin which will take account of the capacitor C3, and that pole, what is the residue? 3 by s, plus what you will have here is s square plus 8, then s and a constant. What is this constant? It is 5s square plus 24 divided by s squared, with s squared equal to minus 8. So, 16 divided by 8, that is 2. All right. Therefore, therefore, my network is the following. What was this? C1? 1 half. Then I shall have a parallel LC and the capacitor C3. C3 is obviously 1/3. And what about this? I always prefer to do it like this. There is absolutely no scope of a mistake. S by 2 plus 4 by S, and this is an admittance. So, the capacitor must be half and the inductor must be, pardon me, 1 by 4. The product should be 1/8. Is it okay? The product should be 1/8, LC product. So, 1/4 and half is 1/8, and the problem is solved. There is, as I said, there is no scope of mistake in this step by step procedure, and as you can see, the numbers involved, there are cancellations of constants, there are cancellations of s, which have to come naturally. Cancellations have to come naturally, because if the function does not have a pole, it must have a 0. All right. So, this is a consequence of the properties of an LC network. The next problem is 11.5. We skip 1. 11.5 is a slightly tricky problem. It says the input impedance for the network shown, the network is this. You will see that almost common sense will solve this problem. This network, input impedance of the network shown is Z in equal to 2s squared plus 2 divided by s cubed plus 2s squared plus 2s plus 2. And it is also given that Z0 is an LC network. Z0 is an LC network. You are required to find out an expression for Z0 and a synthesis for Z0 in Foster series form, that is Foster 1. Okay. This is the problem. Given the configuration and given the input impedance, you see the input impedance is not purely LC, because it contains a resistance. Z0 is LC, but it is an LC network paralleled by a resistance. You are required to find out an expression for Z0 and a Foster series realization. Okay. Capital R is not known, but it can be found out. Okay. This is the common sense that one has to apply. You see, Y in, the admittance, is equal to Y0, the admittance of Z0, plus G. Okay. This is sum of Y0 and Z. So, Y in of J omega, okay, real part, obviously is equal to G. All right. And you notice that the expression for Y in is s cubed plus 2s squared plus 2s plus 2 divided by 2s squared plus 2. All right. What is 1? How do you know? You have to, so for y0 is this minus g, and you have to find the value of g such that y0 is LC. It is obvious from here that if you subtract 1 from here, then you get s into s square plus 2 divided by 2 s square plus 1. Is this obvious? And this is LC. Okay, this is an LC admittance, and therefore G must be equal to 1 or R is equal to 1.
When we do it straight from there, the real part of y and g omega should be equal to G. We calculate from there.
Yes, we can find out from here. Yes, we can find out the real part, but a common sense helps, because we do observe that this can be written as 1 plus this. Otherwise, you would end up in finding m1 m2 minus n1 n2.
Because denominator is real.
Yes, sir.
So, sir, the only real
Denominator is real?
They put that equal to G omega.
Okay,
So 2x by 2x minus
quite so, quite so. In any case, common sense is the strongest instrument that an engineer has, and you must not hesitate to apply it. Wherever you apply it, it is rewarding. Okay. Anyway, so we know G equal to 1, and incidentally we also know what is y0. y0 is s times s square plus 2 divided by 2 s square plus 1. And at this point many of you forget that a specific form has been wanted. You can expand this in partial fraction and get a realization, but that will not be the correct answer, because it specifies that synthesize Z0 in a Foster series form. So, do not realize this. Take a Z0. Take Z0, 2 s square plus 1 divided by s into s square plus 2, and you expand in partial fraction, because we want a Foster series form. And obviously, the residue at the origin, there is a pole at the origin. Residue at the origin is 1, okay, 2 into 1 s into 2, plus, is there a pole at infinity? No. So, s square plus 2 s, and what is the coefficient? 1, okay. So, Z0 is obvious, it is a 1 farad capacitor and a parallel combination of 1 farad capacitor here and half Henry. The product has to be 1 by 2. The problem is solved. The next problem is 11.6. Okay. We will not do all of them. Let us look at A. It says indicate which of the following functions are either RC, RL or LC impedance functions. Since we have not done yet RL, we can answer RC and LC. Let us see. The first function is Z of S. It is an impedance equal to S cubed plus 2S divided by S to the 4th plus 4S squared plus 3. Now, you have to decide whether it is RC, LC or RL. If it is RL, we do not know yet, but let us look at it. Now, obviously you see it is an odd rational function, is not that right? It is odd, therefore, it cannot be RC or RL. It has to, if it is at all realizable, it has to be LC. Let us look at that. S times S square plus 2, if you can factorize, do that. S square plus 1, S square plus 3. So, it can be realized as an LC, because the poles and zeros alternate 0, 1, 2, 3. Okay. Part B. B is Z of S. Now, this is a polynomial divided by a polynomial. It is a biquadratic. If you can find the poles and zeros, obviously the numerator is S plus 4, S plus 2, and the denominator is s plus 1 s plus 3.
This is not an odd, that is not odd.
No, it is not odd, therefore it cannot be LC. It cannot be LC, it is either RC or RL. First critical frequency is a pole, the last critical frequency is a 0, and the poles and zeros alternate 1, 2, 3, 4. So, RC. Okay. Part C is simply the reciprocal of this, and you shall see later that it is RL. RL has exactly the RL impedance has exactly the property of an RC admittance. Let me put it down here to be shown. ZRLS is, we use the symbol triple line with an F, form equivalence, is the same as YRC of S. And in the morning we saw that YRCS has to have the first critical frequency a 0 and the last critical frequency a pole, and therefore C qualifies as RL. D. Now this is a common sense question. S square plus 5s plus 6 s square plus s. It is not an odd polynomial, right? It is not an odd polynomial, but denominator is not Hurwitz. Why not? S square plus s is not Hurwitz. Where are its roots? S times s plus 1. So it is Hurwitz. Now as I said, the common sense. You notice that there is a cancellation. No further efforts are needed. You see, this is s plus 1, s plus 5. Oh, okay, there is no cancellation. S plus 3 and s plus 2. Now 0, 0, 1, 2, 3. No, poles and zeros do not alternate. So what is the conclusion? Whether it is RC or RL, poles and zeros must alternate. They do not alternate, so it is not LC, it is not RC, it is not RL. Can you say that it is not realizable? No, you cannot say, because it could be RLC. How do you determine whether it is RLC or not? Whether it is realizable or not? Give me one test which will determine. Other things are obvious. Yeah, positive realness, but positive realness requires several testing. It requires to check whether the function is real for S real, whether it has j omega axis poles. All other things are obvious, isn't it? It's real for S real. There are no poles on the j omega axis, or there are? There is a pole on the at s equal to 0. Is the residue real and positive? Yes, residue is 6. Therefore, it is real and positive. That part is satisfied. What else? Only the real part. That's right. So you have to find out a of x, which is m1 m2 minus n1 n2. So it is 6 minus x, then minus x, all right, m1 m2 minus n1 n2, that is plus 5x. Is that okay? All right. I have skipped those steps. I have not written 6 minus s squared equal to minus x. No, 6 plus s squared equal to minus x. So 6 minus x, in the denominator s squared, that is minus x, then m1 n1 n2 5s squared minus 5s squared, so it will be plus 5x. This is equal to minus 6x plus x squared plus 5x. This is equal to x squared minus x, equal to x into x minus 1. This is not necessarily greater than 0, necessarily, and therefore the function is not pure, it is not realizable at all. Okay. If a function is not RC, is not RL, is not LC, it does not necessarily mean that it is not realizable. You have to apply the PR function testing. Then E as you can see is simply the reciprocal, of the function at D. Since D was not realizable, E is not realizable either. Oh, I am sorry. All right, then we require a consideration. I am sorry I ignored the. It is LC. Let us write it down. S square plus 3 S square plus 2 S times S square plus 1, because poles and zeros do not alternate. Can we say that this can still be PR? Can this still be PR? Can this still be PR? If it is an odd rational function, and it's PR, it should be realizable as LC. It is an odd rational function, not realizable by LC, therefore it is not PR. It is a non-PR. Is the argument clear? Logic clear? All odd rational functions which are PR can be realized by LC. Alright. If it cannot be realized by LC, it cannot be PR. Okay. If I repeat it twice, I will create sufficient confusion. So, we will not.
Why don't we able to realize these?
Realize D.
So it's also odd even by odd.
D is not even by odd, no. D is denominator is S squared plus S. Okay, the next problem is 1110. Because others involve RL functions, so we will not do that. 1110, for the network shown, there is a network V0, 1 ohm impedance and admittance Y and a resistance 1. The output is V2. It is given that V2 by V0 is equal to 1 over 2 plus Y. Is this obvious that it is 2 plus Y? The admittance here is Y plus 1, so the impedance is 1 by Y plus 1. You see, 1 by Y plus 1 divided by 1 plus 1 by Y plus 1, which is exactly 2 plus Y. And this is given as S times S square plus 3 divided by 2S cubed plus S squared plus 6S plus 1. You are required to synthesize Y as an LC admittance. So, the first thing would be to find out Y. 2 plus Y equal to 2S cubed plus S squared plus 6S plus 1 S times S squared plus 3. Find Y from here and synthesize it. I will skip the algebra and Y, my solution is S square plus 1 divided by S into S square plus 3, and the solution in the Y form, any solution is okay. So, I take Foster 2, I am sorry, yes, Foster 2, and the solution is 3, then a series combination of, I hope I am right, 2 by 9. I have worked out some other problems, but I want to take the time to solve a more interesting problem. All right, let us look at 1111 first. I don't have to. Okay, let's solve 11.11. 1111 says synthesize by continued fraction the function y of s equals to s cubed plus 2s squared plus 3s plus 1 divided by s cubed plus s squared plus s 2s plus 1. There is nothing much in this. It just turns out that if you carry out the continued fraction expansion, the final result is this. It is a lucky affair that it works here, it may not work. This is the final result. But as I said, I want to take a more interesting problem, and this problem is as follows in the rest of the time. That is why I was looking at the what's. We have been given a pole 0 plot. This is in fact the last question of this chapter, chapter 11, last question, but it is not here. It is not here. I forgot to do the third page. There is another page. But anyway, let me pose the problem to you and then try to solve. There is a lot of common sense that is involved in the solution of this problem. I have been given a driving point impedance function which has not been specified to be LC, RC or RL, but its poles and zeros are given, and the poles and zeros are located, all of them are located on a line parallel to the j omega axis, at a distance of 1 from here, all right. And it is given that there is a pole here, that there is a pair of zeros here where this distance, this point is j1, naturally this point would be minus j1, I will not show that. Then there is a pair of poles here where this distance is j2, j root 2, not 2, j root 2, okay. And finally there is a pair of zeros here where this distance is minus j root 3. I am writing it below because there is no space here, okay. That is all that is known about the impedance. Now you are required to synthesize this impedance. Obviously, do you understand the problem? The synthesis, the problem formulation is not complete. There is something missing. Can you tell me what is missing? The constant term. So what we can do is to synthesize it 2 within a constant multiplier, okay, and we will assume that the multiplier is 1 for this problem. 1 is the simplest number, it is a very nice number. So the first thing is that we can synthesize 2 within a multiplier, a constant multiplier. Second, the poles and zeros are neither on the j omega axis nor on the real axis. There are complex poles and zeros, okay. So let us see what we can do about it. Let us write the impedance function 2 within a multiplier, constant multiplier. So let us write the impedance function. The pole, there is only one pole at minus 1 which will contribute to the factor s plus 1. The 2 zeros at plus minus j1, that shall contribute to s plus 1 whole squared, s plus sigma 0 whole squared plus omega squared, that is equal to 1. Agreed? There is a purpose why I am writing it in this form instead of s square plus 2s plus 2. I could have done that also. Then the poles, the next pair is a pole s plus 1 whole squared plus 2, and the next factor is a 0 at s plus 1 whole squared plus 3. Do all of you follow this impedance function? How I wrote this? By inspection, by just looking at it. That is why I chose these nice numbers root 2 and root 3, so that the square could be a whole number. Okay. Let me write it down. Z of s equal to s plus 1 whole squared plus 1, s plus 1 whole squared plus 3, s plus 1 whole squared plus 2. Obviously, the function, if at all realizable, if at all PR, it would be realizable as an RLC, neither LC nor RL nor RC, because the poles and zeros are in general complex, therefore RLC network. Now, we have not learnt RLC network synthesis in general, but this problem is of a type which can be solved by a knowledge of LC networks, because you see that if you put s plus 1 as a new variable p, okay, and you say z of s equal to, let us say, z1 of p, then you notice that z1 of p is equal to p, a new complex variable, p times p squared plus 2, p squared plus 1, p squared plus 3, and this is an LC network in the p plane, in the p plane. Okay. Therefore, I can synthesize Z1 of p in the p plane. Finally, I shall replace p by s plus 1. Let us see. Z1 of p, have you understood the philosophy of this? Why did it occur? Because the poles and zeros were on an axis parallel to the j omega axis. Similarly, had we been given poles and zeros on a line parallel to the real axis, negative real axis, okay, we could have done an RC or RL. Okay. This is a very popular question. Okay, Z1 of p is p square plus 1, p square plus 3, p times p square plus 2. What would you like to choose for its form? Foster 1, Foster 2, cover 1 and cover 2. There is something interesting there also. Minimum amount of calculation. I don't want much of calculation. F1, even cover is not bad. Look at cover 1. P cube plus 2p, P4 plus 4p square plus 3. Let us see, this is an impedance. So, P4 plus 2p squared, 2p squared, cover 1 continued fraction starting with the highest powers. We could do that because the function has a pole at infinity, otherwise no. So, 2p square plus 3, p cubed plus 2p, p by 2, this is an admittance. So, we get p cubed plus 3 by 2p, 3 by 2. So, half p, remainder 2 times 2 is 4 minus 3, okay, half p, that divides 2p square plus 3. So, we get 4p, is that right? 2p square, and this is an impedance, then 3 divides half p, so we get p by 6, p by 6, isn't it? Okay, this is an admittance, and half p, the remainder is 0. So, my network therefore shall be an inductance of 1 Henry in the p plane, okay, in the p plane. Now, this will be confusing. So, we write the impedance and the admittance for the capacitors. This is, no, we don't do that to confuse. We don't confuse. We simply write, just a minute. We simply write P. Shall I do that? There is also a confusion. I write directly in terms of S. Why go to all this? You see, I need an impedance P which is S plus 1. So, I get 1 and 1, S plus 1. Then I need an admittance of P by 2 which is S plus 1 by 2. So, I get parallel combination of a capacitor and a resistance. Tell me what is the value? Half and 2, not 1. Okay. The next one is 4P. So, I get 4 Henry inductor and 4 ohm resistor, 4S plus 1. The next is P by 6. So, I get a parallel combination of 1 by 6 and a resistance of 6, and the rest is an admittance 0 which is impedance infinity, and therefore, the function is done. Okay. And that is all for today.